Thank you. This is what we're doing here today, in case you thought it was design fashions over there. You have to pardon me, my voice is gone, which is typical. Oh, got a little ringing in the cough. Okay, thank you. So, I have multiple topics, and if we scoot right through them, we can actually do this in an hour or so. But at the end of each of those, I have made an allowance for questions, and so you'll see the little thing come up that says questions, and that's when we can engage in some conversation. So, do I just push the button?
Just press the button.
Okay. First topic is the B1 with the transformer. Those of you who are familiar with the first watt B1, it is simply a preamp with an input selector switch and a couple of volume controls, and they are buffered, or the output of that goes to a little impedance buffer which has the unity gain voltage, but which gives you a low output impedance. It's a nice little product, fits its own little niche in the marketplace. It has no voltage gain, which is an impediment to some people. And so at this exposition, I have brought two examples of B1s that have voltage gain. And the first one of them is the one that uses a transformer. And here's the simplified schematic of it. On the left-hand side is what a normal B1 looks like. It's got a switched input, it's got a volume control, it's got a couple of resistors for numerous convenience in terms of seeing to it that it doesn't misbehave, and it's got a little adjustment in the middle for DC offset so that you can direct couple it with very, very low offset. And then it drives a transformer, and this is a line level transformer, the kind of thing that we have seen before. In this particular case, it would be either a Jensen or a Schematic, and these are have got 4 coils to them, and they are rated at 150 ohms per coil. And this one is configured as an autoformer. You drive the bottommost coil, depending on where the switch is set, or maybe the 2 bottommost coils, and these things are just stacked, and they create voltage gain where none existed previously, and they do so passively. So an autoformer can be used, in this case, depending on how it's switched, either for a gain of 4 times voltage or a gain of 2 times voltage, 12 or 6 dB. And then there's the output. And the other thing that's different about it as a B1, and B1 had so little gain that I didn't have to use a log taper pot on the volume control. But this one having gain, I had to go out and buy some conventional log audio taper pots. Otherwise, you crack it open and your speakers fall out on the floor. And, here's a picture of it. It looks exactly like an ordinary B1 until you get to the middle of the board, which is usually a vast empty space in a B1. And there's 2 transformers mounted there, along with little jumpers that allow you to set that 6 or 12 dB gain. And in this case, I've tried it with 2 transformers brands, and I've got some specific model numbers that you can run out and buy. These are the Schematics, and the others were Jensens. And again, I've got some part numbers in case you want to do the same sort of thing. The FETs involved here are my favorite Toshiba 2SK170, 2SJ74, the ones that everybody's charging so much money for, unless you're buying the real ones from Linear Systems, which is a recommended source, and you can get those through the DIY audio store on those occasions where they're both available. Another shot of the same thing. Again, you can see the little circuit. It's just a buffer. It's very simple, no feedback, very unprepossessing. And in this case, the Schematic transformers. This is a CMO Q4PC, I think. They go for about 25 bucks. The Jensens go for about 30 bucks. I have chosen the Schematics because they're ever so slightly better in terms of the performance, and they are $5 cheaper. Here's the transformer. This was set with a 6 dB gain setting, which is the best setting. And you can see the distortion versus output voltage. And the bottom here is 0.0001%, which we all recognize as being pretty good. And as you can see, it skirts down into that zone, does about 0.0008% distortion at 1 volt. Down here, this is partly transformer distortion and also is partly noise, because we're sitting on my bench, isn't the quietest bench on the planet. And so we're starting to pick up a little noise as the relative level of the voltage, in this case, 1/10 of a volt, goes up. But even though that's starting to show up, it's not something that anybody's going to notice, I don't think. As the voltage goes up, here we are, climbing up above 10 volts, and it starts to have some distortion, and then basically it's clipping at about 16 volts output. Here's the distortion on that transformer versus frequency. The distortion characteristics of transformers are slightly problematic because, especially at low frequencies, they start losing their inductance, and so their distortion goes up, and in addition to that, whatever's driving them is having to work harder. So you're starting to see it reflected in the numbers. And this is at a volt output. You can see as we go below 100 hertz, we start seeing some of that transformer character. And actually the same sort of thing up at the top, where the capacitance of the transformer winding starts to creep into this also. Oh, well, that was easy. Any questions?
What's the output? 2 minutes past 3. We didn't miss anything?
Output impedance, depending, is either 100 ohms, no, I'm sorry, 200 ohms or 400 ohms. For the higher gain one, it's theoretically that, because the buffer, well, actually, it's even less than that, because the buffer is about, the buffer's got about 30 ohms output. So at high gain, it's 120 ohms, and at 6 dB, it's about 60 ohms. It's plenty low. I mean, anything else? No, that was easy. Okay. Now, then the other way of getting this, besides doing solid state circuitry, or in this case, maybe using some anyways, is Mr. Mura, the most famous audio critic on the planet at Stereo Sound in Japan, is a very, very nice guy who gifts me interesting things. And in return, I try to do something with them and then send them back for him to play with. So there's a nice relationship. He sent me a box of the Korg new tubes. This is something that's actually been around for a couple of years. It's a triode in a very, very teensy package. It looks like an integrated circuit. But it's a real triode with real cathode that's heated and a real grid. I mean, and the curves that are, I mean, it's a triode. It doesn't run a lot of current. It doesn't need a lot of voltage or anything like that. But it does generate gain, and it does so with the character of a triode, which gives you some adjustability over the distortion character of the part itself, much as in the way we've seen with other triode projects, but also the SITs and some other things where we can sit around and play with the load line and adjust the second harmonic character for various amounts or nulled or even opposite phase. So Korg actually had them manufactured by Noritake, the outfit that makes our displays on our preamps. When you see all the little knobs and everything on our preamps, there's a display there, especially if you're using the remote, and you see that there's this nice blue electrophorescent kind of quality to this. What is monster is it's actually a gas display in a handsome little package, and they have somehow adapted this high emissions off of a cathode effect into making a triode tube, so that it doesn't have to draw as much power or operate with as much voltage as an ordinary triode, and it glows blue, just like their displays. And here it is here. Now, it looks a lot bigger than it is, because it's only about this big. It's the size of a larger sort of integrated circuit. You can see the pins right there. But your typical microprocessor is probably a little larger. It's actually in a glass envelope. If you look at it, these square pad areas here and there. This is a dual part, by the way. There's 2 triodes in it. Those parts are the actual heater / cathodes, just like you would see with a conventional triode, like a 300B or something, where the cathode is also the heater. And then there's some pins that form it. There's a grid and there's a plate, and it's a real tube. But it's kind of unusual in terms of the size, form factor, power, and voltages. It was created for Korg to do special effects. Korg is a synthesizer company, among other things, and if you have a synthesizer, you might just want to dial in some tube sound, and that's precisely what this is for. And tube sound is the operative phrase. This is the characteristic of this part. First thing you see is it's got those characteristic curves that you're used to seeing on triode tubes. I mean, it's a real nice, clear picture. They were clearly shooting just at this effect, and the design was strictly around it. You see, first off, there's a line, a dotted line along there, and the dotted line says, don't operate the tube to the right and above the dotted line, because it's only rated at 1.7 milliwatts worth of power. And this is not going to drive anybody's single-ended speaker. And if you look at the current, you see at the top of the scale is 200 microamps, or 0.2 of a milliamp, or you see what I'm talking about. It's a very tiny amount of current. But the plate voltage is fairly decent. You can actually get up to some pretty high numbers, but because of the dissipation figure, you really can't do much when you have current going through there at the same time that you've got a lot of voltage. So you're constricted down into this lower left-hand corner, more or less, the area between 20 volts or so and down to about 0, and from 0 to approximately 40 microamps. However, if you buffer this part, both at the input and the output, then these currents and voltages are enough. And Korg actually offers up a sample schematic that you should like start thinking about first before you do anything on your own. And I mostly hewed to it because after I screwed around with these parts long enough, I realized that whoever did the work originally really knew his stuff. There wasn't much improvement that I was going to make on it at all. That didn't mean that I didn't stick my signature on it somewhere. And in his case, he had put some nice JFETs on the input and output because the input impedance is not as high as your ordinary triode, and the output impedance, like a regular triode, is very high. You can't use it for a lot of things. So he had put FETs there, but he'd biased them up through resistors. Oh, well, I can at least make one improvement there, which is I bias them with constant current sources. So you see an input buffer, which is the upper JFET just below the plus F, which means plus filtered voltage, and ground. And then down below it is a FET run at what's known is a constant current source where the gate and the source have been tied together. So that's just a constant current source. Gives a little bit better drive and a little lower distortion than using a resistor in that spot. That's about it. Almost the rest of this is pretty much along the lines of what Korg did. I regulated some things a little better, and there's more capacitance in the power supply and so on. But this is the circuit. And the JFETs in this case were the 2SK370 Toshibas, which are the same as a 2SK170, but in a slightly smaller package. And it just so happened that I have a big box of those, and I decided to use some up. So here's that tube mounted up in the same kind of B1 that we looked at a little earlier, except instead of a transformer, we've got this micro tube. If you actually, I have one of these here. In fact, I have both of these models here on display, one with a transformer and this one. But if you actually look at it, you look in there, and it's glowing blue. And they're very clear about the amount of bias current that you should be running through it, which is only 1.7 milliamps as a heater. This thing could run on batteries for a very long time. It's supposed to glow blue, and they're very clear. If you get it glowing red, you aren't going to have your tube for very long. So don't, you know.
So don't red plate it, huh?
So don't redline it. And mostly what you see, this is powered by a little switching supply, you know, the kind of thing that sits on a desktop. And you can see the little cable coming in the back. And I went to some trouble, which I always do with switching supplies, to filter them. So you have a 3-set filter just to get switching noise out of this system. And then the rest of these filters are stuff that are kind of, these capacitors that you see are just stuff that's intrinsic to the needs of the FET. It's got, I mean, not the FET, but the triode. It's got, oh, we want some decoupling on the heater, and it also, they tell you, oh, it's slightly microphonic. Now, I beat on these things, and I did not hear any microphonics, nor did I see it on the scope. But I talked to a guy who said, oh, no, it's terrible like that. So they do advise, though, that you fasten the thing down just a tad, and I put some hot glue on the tip there, and then it was just fine. Not that it wasn't good already. Anyways, the distortion waveform is what you would expect from a triode biased in a particular direction. You see the fundamental here, this is at a volt, and you see the secondary, not secondary, but the distortion waveform after the analyzer has removed the fundamental. The green thing is very, very tiny thing that's embedded in that red waveform. And it's what's left over after you remove the pure waveform. It's the distortion of the unit. And if you look at it, you see that the peaks on this are match up to the peaks on the top. And you also see that the peaks on the bottom also match up to the dip on the top. This waveform is twice the frequency, but this has what I call a particular phase. This phase is positive second harmonic, defined as it has a peak on the distortion waveform at the same time that the waveform is peaking positive. If it were doing the opposite, it would be a negative phase second harmonic. That is my own little nomenclature because the rest of the world either hasn't figured it out or doesn't care. However, this circuit is an inverting circuit. If we go back to it, and you look at that triode, you're driving the gate, it's run in common cathode mode, the signal comes off of the plate on top of that little triode, and that signal is absolute out of phase. So when you use this, you have to flip the phase someplace after the circuit. When you do, that positive phase that we talked about here becomes negative phase second harmonic. In other words, if you flip both of these, you'll suddenly see that the amplitude is going down at the peak of that. In other words, that would be there, and you notice it's in the opposite direction. So you flip it, and you now have, you've corrected the phase, but you've also changed the phase to a negative second harmonic. This is a particular value because the sound of triodes is that of a beast which has a nice high second harmonic content. In fact, it's quite pure. As you can see, there's not a lot of other harmonics there. That's a fairly pure second tone. But if you run it in a negative phase, you will tend to notice certain things. And I don't have any scientific papers, nor have I written any, on this subject. But there's a lot of evidence which hasn't been collated particularly that people experience the following things in comparing the sound of something that has a second harmonic versus the sound of something with a positive. The negative second harmonic has a tendency to make the signal soundstage back off a little bit and has a little more depth and sometimes seems to have a little more separation in space between instruments. And this is all on fairly simple material. If you are playing Symphony Fantastique, you might not notice it. But if you flip the phase so that you have a positive second harmonic, things move in a little closer. The vocal might just be a little more in your face. You get to choose which way that goes because you can actually, even if you're inverting the phase absolutely, you can still adjust the the load line of this part so as to accomplish either of those. The same way that we did with the SIT amplifiers that First Watt built. In fact, this particular calibration is approximately that would give you the SIT1 characteristic for second harmonic with an amplifier that's got a 20 dB voltage gain. So you hook this up to a an amplifier of that type, and you get a certain amount of that quality that the SIT-1 was famous for. Oh, okay. Here's that distortion versus amplitude. Down here, like 50 millivolts or so, you're looking at 0.1% second harmonic. As you go up around a volt or so, you're in the 1% plus region. Again, you can adjust these things. There's actually a pot in the circuit and on the real ones where you can make this go up and down and so on. You can play around with it quite a bit. This happens to have been my favorite setting in terms of listening, and also had the nice smoothest curve when you got up to higher amplitudes. So I chose it as my example. So this is the kind of thing when a guy goes, oh, I just love this amplifier, and I'm going, I'm looking for a nice tube preamp to drive it with, to warm it up. Actually, this is the kind of product that one would consider. These are now available. Pete Millett, who hangs out quite a bit or is available at DIY Audio on occasion, but also has a spot on eBay where you can buy these, and is a reliable supplier, sells them for $50 a piece. You get 2 channels on one. They're easy to work with. You follow the schematic. They do exactly what you think they're going to do. And I've got one playing, but I've been using them for a couple of months now. It's really a nice piece. Not everybody's cup of tea, because in fact it's creating a special effect, which it was designed to do. Oh, there's the gain versus frequency. It's got plenty of gain. In fact, I couldn't really get it to have less gain without doing something wrong with it. Once again, the people who worked the example circuit up did a very careful job and pretty much nailed it. But it goes out, it's starting to drop off. Let's see, it's a little over 3 dB down at 100 K. It's got plenty of bandwidth. Better than the specs in the data sheets. Okay, questions?
So, if I understood correctly, that this thing has maybe 100 times as much distortion as the previous transformer version?
No.
No? I read it wrong, huh? Because
Yeah.
you got over 1% very quickly, and the other one topped out at 10%.
Oh, yeah, but I mean, they're 2 different beasts entirely. The idea on the transformer piece basically is to have quite low distortion. And so we saw stuff that got us down into the triple O range, but it starts falling apart at the extremes and as the amplitude goes up. But it's still quite low relative to this, where it's intended that you're going to immediately go right into the zone where you're between 0.1% and 1%. Is that what you were saying?
But it's all second harmonic.
It is second harmonic. You get well above a volt, you start seeing other stuff, but it's designed to operate in that region.
In that graph that you showed, that showed a nice little dip in the 0.1%, what signal level was that thereabouts?
Oh, that was the signal level on the horizontal scale.
Okay.
So it was in volts. So it was like doing a little over 1% at 1 volt.
Okay.
So at that distortion, then a beast of 1,000 new tubes isn't likely.
I don't see why not.
Well, let's see it next year. Huh?
Well, I'm sure that your budget will float that.
When you send it back to the guy in Japan, what do you think?
Oh, that's a good question. I haven't heard back. But he's a very, very busy guy. He is going to visit us in January, however, so any way it goes, I'll be finding out more then.
Do these degrade like normal tubes? Can you replace them if they've degraded over time?
I have no idea about the lifespan on these, but they don't run hot, and there's no real energy involved, so I would expect that they last quite a long time. I can tell you that the displays that we've been making for, and Wayne would be able to tell me more accurately, but probably 20 years, they hold up fine. And these are ones that are like designed to really put out some light. So, I think it's real reliable. There is only one manufacturer. It's a very special piece. So, you might want to buy 2. Yes?
Any idea what the pricing is on the individual tubes?
$50 for 2 channels. And that's on eBay right now. You can look up Korg new tube, and Pete Millett is selling them.
Did you run it off the 20-volt supply?
I ran it off a 24-volt supply, but I regulated down. The actual voltage that I ran the plate is approximately 10 volts, which is the midpoint. You'll notice that it was loaded into a very high impedance, 332K, which is high, okay? And there's only a few microamps going through there. It has a usable range over quite a bit higher or even considerably lower. This did seem to be the sweet spot. Once again, I got the best looking second harmonic curve. And I was really shooting for, the most purity that I could get over a broad range there. And so all the adjustments were associated with that. Okay, well, maybe we can turn it into a project that you can buy at DIY Audio. I mean, I'm not too sure at this point, but it's a really cool thing. It does sound great. So there are Siegfried Linkwitz. Siegfried is my neighbor. I live up on the coast, nicely on a beach, and Siegfried is at the far end of the beach. He's not there all the time, but he's there enough that I get to waltz on over and sit on his back deck, and we chat for an afternoon or two. And Siegfried is good company, by the way, just in case anybody hadn't known that. And the other thing is that his wife serves up great snacks, which is largely why we're at his place instead of mine. And so if you followed what he's been doing, I mean, Siegfried is very much involved in putting together designs that are very innovative with regards to mostly how they spread the waveforms, the dispersion patterns that they have, how they paint the room or illuminate the back wall and so on. He's very interested in that, and he puts a lot of analysis into it. He's an ex-HP engineer, microwave guy. So when you look at the baffle on his speaker, what you see is somebody who used to design microwave equipment, because he's stolen numerous of the ideas to get those shapes. He not very long ago came up with what he considered to be his uber budget piece, and it was called the LX Mini. And it was a pair of Seaz drivers. Actually, the drivers are quite expensive, but the rest of it can all be bought for a few bucks at Home Depot. Plastic pipe and coupling things. I mean, he was very much, he puts a little handle on it, you can carry it around. What you have is a full-range Seaz driver, which has been, it was designed for actually conferencing systems, and a quite powerful little woofer that Seaz makes, and he put them on top of a tube. As I say, if you've gone to his room, you already know more than I need to tell you. This is initially was designed for it was a biamped piece, not an active crossover, and Siegfried, instead of rolling up the 100 op amps or so that it takes to get some of these curves, decided that he would embark upon using DSP for it. And in fact, that is how the product has been presented. And it works great. The thing was, is I'm sitting on Siegfried's back deck eating melon, and I said, so, how's business? Well, he's got some real interest in China, and he's got a guy in China who really wants to distribute these, and there's a strong potential for some, action here. And I said, oh yeah, well, that's really interesting. Is, have they asked for the analog crossover yet? And he goes, well, no, and I don't really see why they would. This is very adequate crossover. This is, this is a perfectly fine. Don't you agree? He'd say, this is a very fine. Absolutely, it's great. Well, I asked that question because I have some history with DSP stuff going into Hong Kong, and my ex-partner from many years ago, and Wayne, who was here talking, did that design work. There was a DSP crossover in this very large quadrature speaker, and they got them off to distribution in China, Hong Kong, and one of the things that came back was, oh, can we get the analog version of that crossover? And Renee, my ex-business partner, said, no, I don't think so. You're just going to have to live with it the way it is. years later, somebody else who will remain actually unnamed did the same sort of thing on a loudspeaker. And I had actually done an analog crossover for him initially, but he decided to go with DSP, and there's reasons for convenience and expense to do that. And when he sent it over to Hong Kong, or we was dealing with Hong Kong, they went, but can we have it with the analog crossover? And so I already knew that the first question that would always come back is that. So Siegfried said, no, I'm not interested in doing that. About a month later, we're sitting on his back deck eating melons again. And he goes, say, I've been thinking about maybe having an analog crossover. And I said, China, huh? So he goes, yeah. I said, well, that's a very complicated curve. This is the curve to an LX Mini. There's the bottom end that you can see. It's got a nice big bump at 50 hertz to give it some bass where that relatively little driver might be deficient. And then you see that the full range is crossed in at somewhere below a kilohertz. That's the purple one. But you also notice that there's little bumps and stuff in here. I mean, little squigglies and so on. Well, in DSP, it's not so hard to generate the little squigglies. And, but in analog, each little squiggle's got another bank of op amps doing it because it's not so easy. It's doable, but you start ending up with lots and lots of active hardware. And I don't design with lots and lots of active hardware or even op amps, in case you haven't noticed. And I said, well, I can't do that, Siegfried. It's got too many squiggles. That's too much stuff. And he goes, well, it's got to have them. And I go, well, I can't do them. Another month or so goes by. He's going, well, maybe we could, And meanwhile, I had thought about it and going, well, maybe I could kind of half-ass do it, and get something going here. And in fact, I did, because I actually occasionally have a slow day. And, you can do a lot worse than working to make Siegfried happy. So I designed one up. Looks like this. In fact, this is it. This is it after Siegfried was done playing with it and tweaking it to his taste exactly. So this is the actual reference edition. And he did make some small alterations in how the curves went. But in this case, gee, you might be familiar or with this pair of FETs, because we just saw them in the B1. They're buffers. In this case, push-pull buffers. Well, they were in the B1 also. And they are just operated without feedback. They have quite low distortion in and out. They behave themselves very well. You have to get good FETs. You might have to match them carefully, and you spend some money there. But, aesthetically, it really does, to me, it beats the hell out of an op amp. And the proposition here is that it's good enough for that task. So here you see the filters that I came up with for Siegfried's speaker. Here's the low pass. Here's the low out. This is the low pass. There's an input buffer, and there's a low pass filter, which is the thing that rolls it off at the top, so that the full range driver can take over. And past that, you see a low frequency equalizer, which is a low pass filter, but which is very high Q, so that it bumps up at 20 hertz before it goes into low pass mode. And at the top, we've got a high pass filter followed by an equalization curve to get something that looks anywhere like the squiggles that Siegfried had. This is the PC board for that circuit. It's all put together in nice modular little pieces. You can see the JFETs. There's one, and there's its opposite. And you've got C1 and C2 and so on. These are the capacitors involved. And, actually, this is the whole thing. Like the other B1 and other kind of products that I've done in projects, well, it's driven by a little switching supply that's off board, and we come in and we filter it real nice to get the noise out of the switching waveforms that are on the power line and get it nice and quiet. This is what it looks like as a real item. This one is not precisely, well, there's been two versions and they are slightly different from each other, but there it is actually in its stuffed up form, for. And you can see the FETs, and you can see the caps, and you can see all the resistors. And there's cute little RCA connectors which mount right on the board that you have to be very careful with, because these big monster cables that weigh a ton can break them right off. However, if you're willing to come up with a cable that doesn't weigh 5 pounds per square inch, then you're probably okay. This is what that crossover does, okay? It's pretty much the same, but it doesn't get the squiggles. Here's the actual traced comparison between the DSP version and mine. You can see on the top end clearly which one's which, because the DSP one's got the squiggles and mine is just these rounded shapes. And down at the bottom, you can see it kind of falls in real nice until the bottom below 50 hertz, where it falls off much more rapidly. And of course, it falls off much more rapidly, but you don't bottom the woofer out as easily either. So it's kind of a give and take. Siegfried actually took this and then measured it acoustically in his setup against for each one, so that he could verify that in fact it was behaving itself. And down the bottom is the analog circuit. On the top is the DSP. When you see these monster dips in the middle is where he's flipped the phase to assess the null. As you may know, Siegfried is big on, if you can get a really nice null when you flip the phase between the two high and low pass, then you're assured that the phase is very good when you put it back. And so there's good assurance of a high degree of phase, I wouldn't say phase coherence, but at least a phase that's behaving itself. And there it is. So the bottom one is the analog, the top one's the DSP. If the analog, you can see it falling off a little faster. Up at the top end, interestingly, it's actually got a little bit less of the jumping around from the driver. We decided that in the end that this really was something that becomes more specific to a specific angle, even potentially drivers having some variation. So that when you get really high Q stuff, it's difficult to reproduce it exactly. So by accident in this case, it actually came out a little flatter. There's no guarantee that that would always be the case, but here we are. Questions?
Nice job.
Oh, thank you, thank you. I'm not done. Oh,
We're
okay.
just talking about the curve.
Oh, okay, very good, thank you.
Nelson, does the crossover have the ability to change the output level so you can level match amps?
Yes.
Sweet.
Well, in the case of the three-way, so much gain has to go to the bottom end amp that you just attenuate the others. So the mid and top are adjustable.
Why did you not need to reproduce the squiggles?
Oh, well, I didn't want to. Accident. Well, but I mean, I asked Siegfried, well, how did you get that curve? He goes, well, I put a microphone in front of the speaker. I go, well, you know, but if you move it somewhere else, you can get different results. And in fact, in testing, the chance that he had it exactly positioned as it was in the original tests were maybe not the case. Or as he said also, you can get variations between drivers. I argue at this point that it leads to the conclusion that one doesn't want to chase the squiggles so delicately. And probably Siegfried agrees, but I would leave him to tell you that.
Can you easily add a sub to this?
Pardon?
A subwoofer?
Yes, well, next topic. All right, so no sooner did Siegfried sign off on the sound of the last one, he goes, well, no, I need a three-way. I'm like, Siegfried, you're just feeding on my back here. Okay. And I looked at the curve and I went, oh, geez, I'm going to have to put an op amp in here somewhere. It's going to, nah, I didn't do that. But I did. Here you see, by the way, simulated on microcap. I did work up a circuit where the mid treatment is largely like the two-way, which, by the way, is how he did it when he DSP'd it. And the top end is the same. So at the top end crossover, he didn't have to fool with it at all. Just simply had to, instead of a bass boost, put a bass roll-off on the what is now the mid, and then come up with a different curve at the bottom here for the subwoofer, which is quite a bit of stuff, as you can see. But yet these are unity gain op amps in the simulation, which are buffers. And of course, in simulations, op amps are just perfect. Actually, they're fairly perfect in real life, but you know, we don't always want that. This is the artwork that represented that circuit. As you can see, it's got more stuff, but you've got a sub, mid, and high. It's got it's got volume level control, so you can adjust mid and high. This is true of the other one also. But the sub didn't need one because it needs the most gain in the first place. It's the one where you're never going to be attenuating it. So you attenuate everybody else by comparison. So this is the actual circuit. We have one. I had one, brought one that was tested and gave it to Siegfried today, and they hooked it up and they had a problem. I think that they needed more gain probably on their source. So they had to go back to one that used op amps, but apparently was very similar to this actual circuit. Here's the comparison, once again, between the simple analog version versus the DSP. And you can see that, well, on the top end, it's the same deal with the squiggles as before. The mid-range, you see small variations. You know, you get in the 1 dB here, maybe 2 dB on the extreme kinds of things. But it follows pretty closely. And then on the bottom, much the same thing as before. I wasn't going to worry about that. He's 30 dB down. This guy, you don't have quite the extension below 20 hertz that comes with the original. But once again, that's the way it goes. I mean, we could put a lot more circuitry in there to duplicate it exactly, and I didn't want to. At this point, we'll probably still be tweaking this one. This is not a finished product. We'll first figure out why it doesn't have enough swing, or something didn't have enough swing to drive this today. But, you know, all this is very solvable. Both of these are going to be offered up for DIY. That is to say that I'm not making commercial product out of this. And the exact nature of the kit is to be determined, but it does need the PC board, and it does need the matched JFETs to make it perform as well as we're looking at here. But that's going to be quite modest. So those people, you know, like I say, we'll get the values tweaked up and get the rest of it all done. And it and the LX Mini, probably DIY audio stores, is the logical place to stick it. And so you can look for it there if you have an interest. Oh, here's the actual board doing its thing. You see how neat the layout is on that? I want to tell you that I put a lot of time into making all those things line up so sweet. Questions?
And sorry, I need to ask this. I mean, you spend a lot of time perfectioning those amplifiers. Isn't it a bit frustrating when you see that they come out of those kind of imperfections loudspeakers?
No. Not in the slightest. A friend of mine, or an acquaintance of mine, emailed me and goes, I was talking to, and I'm not going to mention the loudspeaker designer name. He's a great guy, and he's probably right. But he just basically said, I have no interest in amplifiers. They all sound the same. It's speakers where all the action is, okay? And I said to the guy, well, that's interesting. I'm an amplifier designer, and guess what? All speakers sound the same. No, but, you know, I mean, the loudspeakers have their characteristics. And one of the beauties about electronics is you can sometimes, you know, work around and maybe even transcend some of that stuff. Or at least bend it in a direction where it's a little better, it's, you know, from a subjective standpoint.
Did I miss it? Did you mention which woofer you're using for the three-way?
Oh, this is the big Seaz. This is the one that Siegfried has and is his specified piece.
It's the same ones that are using the 521.
Oh,
Yeah.
they're expensive.
Yeah, a couple hundred each.
Uh-huh. They're more expensive than that. Okay. Oh, I'll go back. Yeah.
What kind of amplifier were you using? Amplifiers.
Me? Oh. Well,
Pioneer, right?
you mean on my LX Minis?
Fisher 500.
No, actually, J2s, F7s. I don't play loud. By the way, I haven't heard that three-way crossover yet. Okay, because I don't have an amplifier in my sound room that will drive that woofer. Not these little 10 and 25 watt, you know. I have to get something from the plant. Tell them to send me an amplifier.
They're $250 per driver. Yeah, that's what I was saying, I think.
You look again.
Okay.
Yeah, look again. I got a discount, and it was up in that zone. But they're amazing drivers. What do you want? You know, you're stuck sometimes. Yes? Nobody? Okay. Amp Camp 1.1. You're familiar with the Amp Camp 1 as a concept, or some of you are, most of you are. We were having discussions, Mark and Jason, and the current batch of product. In fact, by accident, we ended up with lots of nice extra boards of the current product that had been revamped slightly, but which didn't fit a chassis alteration that people had in mind. And that's why there's 250-something channels here at the show in little bags, which work just great, but they don't fit the chassis that's projected for this, which is a 2-channel chassis. So you can actually, if you have a drill press and you want to drill and tap 2 holes, you can fit those boards into the newer chassis. That's not that big a deal. But it isn't the clean kind of transition that...
They will bolt into the old heat sinks, it's just there's a bracket in the way. So if you have the heat sinks that are drilled and tapped, they'll work.
I think it can fit. Anyways, so of course, 250 of them had gotten ordered before they informed me that they were changing the chassis. So that's how that happened. However, there was a revision to that design. The actual board itself has been laid out a little differently because the transistors go and power transistors are mounted in a different spot. And it has the previously elusive R15, which was a resistor added on to jump up the bias and give more power because that was determined to be desirable. And so, So this is actually pretty much the old amp camp circuit, but it's got R15 that you can see over here, almost the dead center. That's been added, and it's been laid out a little more snazzily. And it's got some specs. I have changed one other thing, and that is I lowered the gain on it, because I could, and in so doing, I got a little bit better distortion and bandwidth and damping factor for my treble. And I thought it was worth it because when you're running 5 watt, 4 watt levels, you don't need a lot of gain. Most preamps will drive the crap out of that with almost no gain at all. In fact, some of the circuits we've played with on and off have no gain at all for power amps. They just preamps got plenty of gain. There's the circuit. That is the official circuit. There's the official board. And it's been set up because the transistors are now mounted front and aft. And this is designed to be a stereo amplifier. I built one so far. It runs great. We've got it on display, and people can actually use it. And you can see all the gorgeous wiring job that I did right there. And you see that there's 2 channels. Part of the deal here was to go to a chassis which is a little more cost effective, but also to get 2 channels into it and really be able to bring the price down. So in the upshot of all this, we're getting a little bit better performance as a stock piece, but we are bringing it in at a lower price. The back is familiar. The back is fairly familiar, except that being 2 channels, it's got 2 of them. It's got the desktop power supply that plugs into the little thing there. It's got an on-off switch that you see on the top there in the center. And in the middle is an XLR connector. If you have a balanced source, you can drive this thing balanced and you can take it up to higher power levels. So it becomes a more powerful amplifier. And yeah, there it is. Whoops. There it is wired in. You can see there's cables that go to it. And so it depends on how you want to run this thing, but you can plug an XLR in or you can plug in 2 RCAs. But as a monoblock, you get more power. More power being like this. Here's 3 curves, all in red, very conveniently. The top one is the original ACA, run with a 19-volt supply. The 19-volt supply was chosen because it's the standard for laptop computers, and the surplus markets have lots of those things nice and cheap. That's, price was driving a lot of this. So the top curve that you see there was the one that people have been getting all this time. By lowering the gain a bit and having a little more feedback for it, I was able to take that down to the lower curve, which you see, and so you see that the distortion's gone down by a factor of half. And essentially, I think worth doing. But at the same time, 24-volt power supplies are starting to show up, and they're more expensive, but you can get them. And what's driving that is LED lights. The lighting systems for various and sundry that use strings of LEDs are tended to hew to a standard of 24 volts, and all of a sudden, not only are there a lot of 19-volt supplies on the market, but there's a lot of 24-volt supplies. And that extra 5 volts is worth something. You'll notice that there's, the bottom one is really two curves. They're all identical, same amplifier, but it's got 24 and 19 volts until you get up to 4 watts. And at 4 watts, this other guy, the original, starts climbing steeply. The 19-volt supply gets it up almost to 8 before it gets into a comparable position.
24 volt.
I'm sorry, 24 volt. It has got not twice as much power, but getting up toward it. Very nice for just a few volts, and unfortunately, a few bucks more. And that's all going to get worked out one way or the other. But you can go either way, but the extra wattage is available. Below that level, same kind of distortion figures. Except for here. On the ACA and the 1.1 and the 19 and 24 volt, the top one is the original ACA at 1 watt distortion versus frequency. And you see that it climbs at high frequencies. This is due to the Mosfet capacitance on these power transistors is nonlinear with voltage. And when the capacitance varies, that creates distortion. And at high frequencies is where that shows up as an impedance that is comparable to the comparable in difference, so as to create the greater distortion than you normally would see. So the varying capacitance of MOSFETs, power MOSFETs, which depends on the voltage across the MOSFET, is higher at high frequencies because that's where the capacitance comes into play. And when you look at the ACA 1.1, you get the lower distortion number. You see that with the lower versus high voltage, you see a real difference in the curve. The one with the lower voltage goes up earlier and it goes up higher. The one with 24 volts has got those few extra volts, and that lowers the nonlinearity of the capacitance on the MOSFETs enough to clean that up very nicely. And you can see why it's starting to become attractive to spend a little more money on a 24 volt supply, because you not only get more power, but it's cleaner up at the top end. And, oh, so here's the ACA 1.1 run balanced, okay? The other figures that you saw were 2 channels, stereo in a chassis. But if you run the XLR balanced connector in and run it in mono, you get this curve into 8 ohms with the 24 volt, and it gives you 10 watts instead of the, I think it was like 4, well, actually between both of them. I think at the same number, it's climbing up to around 12.5 watts. It's basically not quite doubled. Into 16 ohms, it's also doing a pretty decent job and holding up. Again, these are higher numbers and lower distortion than we're used to seeing on ACAs. Oh, well. Ta-da. Questions? This is in process right now. Mark has been bugging me to get the boards on order and so on.
I bug him for you.
Yes, he's thinking of you all the time.
Is the circuit online?
Not yet, but it will be. Well, actually, that original circuit is virtually the same. R15 added was the only change, and even that's online. It just doesn't happen to be on the artwork.
Actually, you changed another resistor too.
Oh, the feedback resistor. Yeah, I changed the value on the feedback resistor.
The kits will have both the original resistor that was changed and the new value. So you can.
He's finding it easier to throw an extra resistor in than to find the other one
Yeah,
and get it
'cause we
out.
come up with it till after we had all the banks.
I'm sorry, progress marches ahead. I still got more. Oh, yes, go ahead.
What's the output impedance balance?
Oh, it's,
Really low?
yeah, it's like, well, no, not real low. It's more like a 1 ohm.
Yeah, awesome. That's still good.
Yeah. Oh, there it is. The thing about the thing about the ACA, it isn't designed to be the greatest amp in the world. It's designed to be something where a person who's never built anything before can jump over that little hurdle and be able to be successful with it, because we have very little trouble with people, not to mention the fact that the questioner here is the guy who's written or produced the build manuals and the videos and such for this. Anybody know 6L6 standing there? That's Jim Tiemann. And we owe you a large debt, Jim, because if everybody had to wait for me to do it, what would it be?
I'm just the biographer. It's still all you.
No,
And they do sound real good, the amps. I mean, it's really surprising.
And don't sneer at the giveaway ones or the $5 ones that are up here. I mean, both
Oh, those are the originals.
$10 power supply on it. It's got real Toshiba JFETs in it. Those amps in your pocket sound stupid.
One of those Toshiba JFETs at market value is the whole kit, price of the whole kit. And you get 2. Okay. But it'll be all nicely documented, and Jim will be working on coming up with the nice build videos and so on. And there's going to be more coming along in this frame, but we wanted to try to move this one ahead. The biggest thing about it is you can either have it quite a bit cheaper and still cheaper, but even better performance yet. So I think that it's going to be an improvement all around. But they're designed to be a first project kind of thing. The def amp. Last year, I talked about the def amp, and I had, look at it, here's a schematic and so on. The def amp is on display and operating here this year. And the simple circuit on this looks like this. To reiterate what I had to say last year, you've got over here, this is an output stage. I'll point there. That's an output stage with a couple of power transistors. What's special there is that the top one is in this case, a depletion mode power JFET. Depletion mode means that the control voltage that biases it up is, generally speaking, got to be negative with respect to the source. This is in contrast to almost all the Mosfets that we get to play with now and again, which are enhancement mode, where the opposite polarity is required. So that if you have an enhancement mode MOSFET up there on Q3, you have to put a positive voltage to the gate to make it conduct. In a depletion mode part, you have to apply a negative voltage to make it stop conducting, because if you don't do anything, it just is a switch that's turned on. Well, so at about 3 or 4 volts negative, it'll bias up to about 1 amp or so. And if you can find an enhancement mode part whose bias voltage is approximately 3 or 4 volts at that current, if you put them together, they self-bias. They don't require a bias circuit at all. It's perfect. Just like those, when I showed those FET buffers before, you may have seen that the gates are tied together. Those are both depletion mode parts, and they run happily at their own little bias voltage without any circuitry whatsoever. You can't quite achieve that with these power parts, but you can do this. And so it's called the def amp because it's depletion mode, enhancement mode, and it's a follower output stage. The cool thing about it is it's got almost no parts. You can run it without that Z1. That's just there for people who are so crazy they might break it with a high input voltage. But it's literally that simple in terms of function. The only problem here is you've got to go find parts where the depletion mode bias voltage matches the enhancement mode bias voltage. And they're opposites of each other so that it all comes out nice and neat. This is not so easy because not only are there very few depletion mode parts, but trying to find something that even halfway matches is an onerous task. So this is the kind of thing where you'll never see them in production, you'll never see them manufactured. They are going to be for DIYers only because of the selection process required is such a big pain in the butt. So, but that's what's cool about it. It actually works quite well, but most of the, let's face it, the real attraction here is, geez, there's almost no parts at all. That's probably my favorite mantra. In this case, the follower's got to have something to drive it, needs some voltage gain in the amp. You don't have to have voltage gain. I built these without voltage gain, but then the load goes to the preamp and it's got to work real hard. And I didn't want that. So just like we have done elsewhere on things, we're using an autoformer. And I think I showed the autofarmer trick with the B1 where you drive the one coil and they're all in series and now you get some 12 dB of voltage gain. We're doing exactly the same thing here. And where that buffer is driving a single coil of the transformer and 4 times that voltage is appearing at the gates of Q3 and Q4. You got 12 dB worth of gain. You got the follower that'll give you all the current that you might need. You buffer the input because the transformer likes to see low source impedance, and I can't assume that the customer has got one. I've got lots of preamps, and there are a lot of preamps out there that have an adequately low output impedance for this. But it's amazing that a lot of the people who are attracted to my circuits have got tube amps and stuff with not so low output impedances. So it's almost a requirement that we use that. Otherwise, we could just get rid of it. Here's the actual def amp circuit, the one that you can see running up there. And it's got a couple of extra tricks. I do have to control the offset voltage on here with this little circuit that allows me to set the DC offset very close to 0. And oh, I guess that's it. The rest of it, as you can see, is still the same thing. It's uber simple. I did put an output relay on it because it's got a little turn-on thump, so that it turns on, and rather than have the speaker see the thump, I have a delay on the relay and it goes click, and then everybody's happy. Distortion on it, okay, and keep in mind this is a transformer-based piece. You're down on 1/10 of a watt or so, you're 0.01. There's going to be noise down below there, so it'll rise. And then you see that it climbs, and something short of, well, actually, it'll do 20 watts at less than 1% without any complaining. That's around here, that's a perfectly nice figure. This is a no feedback amp. No feedback amps normally do not see such low numbers, but again, nice parts operated without a lot of rigmarole. They don't have resistors on the sources in between the speaker load and everything, so that the performance is actually quite good. It really does justify the extra effort of selecting the parts. Here it is into 4 ohms, and we see that it's coming apart at 50 watts. It's a fairly powerful little amplifier. It will drive your lower impedances reasonably well, and at pretty good distortion numbers. You will see that it has a second harmonic characteristic at modest levels, and that the second harmonic is magically in the negative phase. Well, that's the way I like them. So that's the way I tweaked this one until it behaved this particular way. You can, if you want, tweak that second harmonic out altogether, leaving just a mostly third, or you can tweak it up and make it go in the other direction. It requires extra parts. And also resistance in series with the sources on the power transistors driving the speaker. So it kind of mangles some of the purity of this. Distortion versus frequency. Once again, this is really good. By the way, this is also done with a Cinemag transformer, which I think, as I mentioned, has edged out as to being my favorite. And at low frequencies, yeah, you got some distortion. It's a transformer. But it holds up very nicely, and it's 0.015, and this is at 1 watt. So as things go, particularly for the non-feedback variety of amplifiers, this is a very happy little amp. Frequency response is not so fabulous. It's 3 dB down at like 35K or so, I think. Let's see, is that about right? Yeah. But Oh, transformer, what can I say? The output stage itself will go out to about a megacycle. Now here's something interesting. In times past, at various points, we have talked about the IRFP channel problem. That is to say, there's a transconductance anomaly on IRFP 99XXX series p-channel Mosfets, where the gain kind of just shelves down a little bit at mid-band and then stabilizes and goes on. As you might imagine, when I'm fooling around with these circuits, I take all sorts of different parts and stick them in there to see what I'm going to get. Sometimes I can pretty well predict what I'm going to. And in this case, I knew what I was going to see, but I thought this is a good illustration of this phenomena. If you look at the bottom line, that's nice and straight distortion curve across the band, this is an IRFP 9140, but it was made by Harris. Also, you get the same effect if your p-channel part is made by Fairchild or Ixis, a whole bunch of other people. But if it was made by IR, you get the top curve. And you see that shift of gain, which creates a second harmonic characteristic. I'm not saying that that sounds bad, but there it is. So when you hear about, online, over in South, they go, oh, the IRF p-channel problem. Well, this is what it is. A subtle shift in the harmonic structure that creates more distortion. It disrupts the balance that's been set up by transistors which are otherwise more matched. Questions?
Yes. Okay, is that 9140 problem still a problem with the IR part, or has that changed now that IR's been gone?
Last time I looked, it was still there.
Still there?
Yeah.
So the shade parts that they grab from IR will still have that?
Last time I looked.
Okay, that's all.
Well, you can buy the Harris parts. They are a lot more expensive. You get to decide. All right, there we saw there's the def amp. Now, keeping in mind that a SIT, a static induction transistor, which is a particular kind of JFET, is also a depletion mode part. So when you're thinking about making a def amp and you're going, well, what shall I use for my depletion mode part? You could consider the possibility of an SIT. They're out there at the moment. You can still buy token parts out of Japan rated at 300 and 400 watts and a couple hundred volts and 30 amps. There's some nice stuff. There are some nice legitimate sales guys, people selling these, and anybody who wants to know can talk to me after, and I will refer them to a guy who's reliable. And they cost about $50 a piece, and they come over, and I bought some and tested them. So I know we're good there. The deficit is an interesting amp that's worth trying. It isn't as low a distortion as the def amp, but the def amp we were really tweaking for that. In this case, we're playing the game of listening to the SIT, which has the triode characteristic. But it works rather well. This is the deficit circuit. This is the actual, the values aren't on here, but it's not really important because the resistors and caps aren't really critical at all. You got a buffer. Oh, what are we doing? Well, the buffer's driving the same transformer that we've seen twice before already. You could come up with any kind of voltage gain stage you want. That's not really an issue. But on this burning amp, we are doing transformers everywhere. Partly because I'm so enamored of the Cinemags. They really are nice. And when I'm all out of them, I'll probably switch to something else. But there's the same circuit that you saw with the def amp, except this one is capacitively coupled. Okay, you can see the capacitor at the end. You also look in Q3, that's the depletion mode part, which in this case is the SIT. Q4 is the enhancement mode P-channel MOSFET. So a lot of stuff is familiar, but the bipolar supply is gone, and you see that there's a negative rail and a ground at the top. Oh, what's with that? It's like upside down. Well, there's a reason. Q3, an SIT, has a very low drain impedance. Any noise that shows up on the drain of Q3 at the top goes right through and into the output. It may be attenuated somewhat, but not enough to cover the action. So that if you have bipolar supplies, as with the Sony VFET DIY amps that we've done, you then can understand why we regulated those supplies. One of the reasons was we couldn't afford to have any power supply ripple or noise on the gate, on the drain of the SITs, the VFETs, or it would go straight to the output and we'd have to deal with it. That's my phone that I don't know how to shut off. So the solution in this case is, well, let's just make ground the positive rail. And there you see that the drain of the SIT goes straight to ground, where it doesn't get any quieter than that, so you don't get any noise coming through. And that's why this has a different circuit to it. However, works like glue. And I don't have to have a positive regulator, and that's one more set of parts that I don't have to think about or put onto a circuit board. Here's the deficit. As you can see, higher distortion than you see with the def amp. This is a second harmonic beast. It is designed to kind of be a little bit like those Korg tubes and the other SIT products. SITs are great pieces for generating that kind of like relatively subtle second harmonic distortion and getting a particular effect. It is a special effect, and we make no bones about that. However, it's very pleasant. I'm not here to do anything other than have people be entertained, because that's the actual business that I'm in. So there it is. Like I say, no great shakes on the distortion curve, but totally rational. If you're familiar with single-ended triode circuits, it'll be quite familiar. In fact, actually, this is kind of lower than most of them. Here it is driving 4 ohms. Does a pretty decent job. In other words, it essentially doubles its power into 4. So it can drive some of your lower impedance loads without too much complaining. Distortion versus frequency is really nice, partly because the bandwidth is a little bit limited on the top. But that is the distortion curve. And here's the bandwidth itself, and I think it's 3 dB down at about 60K, it looks like. A little more bandwidth than the def amp, but part of that is that the SITs are very fast pieces, and so we're really looking at the Mosfet that's dragging it down a bit. And here we are at the end. Any questions?
On the standard def, what are the common pieces, the common output transistors? You didn't have anything labeled.
Oh, I'm sorry. Well, on the standard def, I've been using mostly RO85 semi-south, which I have a large quantity of. They'll have to be, won't they? No, in point of fact, there's other parts out there. But it turned out that the RO85 was the most convenient match to the crop of P-channel Mosfets that you see, which the IR parts are like 4-volt VGS parts. And it turns out that quite a bit of the range on that largely matches the range of variation we see on those semi-south parts. And I got 1,000 of them or so. We'll be okay. Now, the def amp and the deficit amp are going to make appearances. Well, the def amp for sure is going to make an appearance in terms of DIY, so that you guys are going to be able to get the boards and the semis and chassis probably as the option, or maybe they'll decide to offer it as a whole kit. But this is something that I was talking about vaguely in the future last year, and we're now at the point where as soon as we sweep some of the other stuff aside, we will stick channels out there for you to be able to get. Also, we have plans. Just one last item. You recall that there were three offerings of the Sony VFET amps that went like that. And then people go, oh, no, I didn't get it. Well, those were the second offering. And then they went like that. And then the third offering went. And then we were like, OK, well, I'm sorry, but that's it. However, the quantities involved were all predicated on the idea that we needed some spares because, well, people are going to blow them up, and then what are they going to do? They'll be crying. We don't want that. So I set aside, about 500 of these parts so that we could repair the kits. Well, so far, nobody has come forward and said, I need a spare. And either nobody's building them, which I don't believe, or they actually are successfully being stuffed and made. Now,
Probably because he put the test points all over the circuit board where you can make sure the voltage is right before you stick your output device.
did myself a favor with that.
Yeah.
But also, those Sony parts are quite rugged. I mean, they don't break easy. I've never taken one out, and I've been fooling around with them for years. And I'm not gentle, you know. It's like, whew. So the point here is that there are Sony parts still left, and half of them are P, half of them are N. But when you look at the deficit amp, I can't quite do the deficit because I can't get a match on the parts. But if I give them a current source, just a constant current source, I get a lot of the same sorts of performance, except that it doesn't drive the low impedances as well. And there's no selection process, there's no craziness. You put them in, you turn the pot till they hit a certain voltage, you got an amplifier. We have maybe 400 channels worth of these that we're going to be able to release here in the coming year. So all of you who are whining that I didn't get in on that, I feel so bad, I think we're going to be able to take care of this. And we're looking at a 10-watt amplifier. But operated without feedback, nice and cool. And we have the transformer front ends, and I think we'll probably come up with an active front end as an alternative. Might even just stick with the active, I don't know yet. But this is all coming up in the next few months. One last round of questions? No? How long did I take?
Let's see, about an hour and 10 minutes.
Oh, yay for me.